Okay, so let's continue where we left before the break. So I think we discussed about maximum likelihood estimation, right? So now let's look at an example. Now consider tossing a deformed coin for n times. Okay, so a normal fair coin would have the probability of 0.5 for head and 0.5 for tail. Okay, now I have this slightly deformed coil. I don't know the probability values for head and tail. Okay, and we're going to estimate this value by tossing this coin for n times. Okay, now each trial is going to be IID sampled from a Bernoulli random variable with parameter p. Okay, so now the probability, let's say C is equal to 1 is for heads and C is equal to 0 for tail. Okay, now the probability that C is equal to some value given P is given as P power C 1 minus P power 1 minus C. Right? So if C is equal to 1, the probability is given by P. The second term is 0. If C is equal to 0, the first term becomes, like first term is 1, so the second term is just what is existing. So if P is equal to 0, then the probability is given by 1 minus P. Now this is exactly the distribution of the Bernoulli random variable, Bernoulli of C given P. Okay, now given a bunch of n trials, like we can just collect these trials and maximize the log likelihood to estimate P, right? So that is what we normally do. So the log likelihood is given by log of product of I is equal to 1 to capital N, probability C is equal to Ci given P. Okay, now this is equal to summation over I is equal to 1 to capital N log probability of C is equal to Ci given P, right? Now I can expand this. There are only two possible values. So whenever the value is, whenever the probability is C, okay, so let's say I have totally n trials, okay, out of which n0 is the number of times C is equal to 0. n1 is the number of times C is equal to 1. Okay, so whenever C is equal to 0, the probability is given by log P. Whenever, sorry, C is equal to 1. Whenever C is equal to 0, the probability is given by log 1 minus P, right? So I can just write this as n1 times log P of C is equal to 1 given P plus n0 times log P of C is equal to 0 given P, right? Now, this is essentially n1 times log P plus n0 times log 1 minus P. Okay, where n0 plus n1 is the total number of trials. Now this is my log likelihood. I differentiate this with respect to P. So I get n1 log P, when you differentiate, it becomes 1 by P minus n0 by 1 minus P is equal to 0, right? So now n1 by P is equal to n0 by 1 minus P. So 1 minus P by P is equal to n0 by n1. Okay, I'm just going to do a bit of algebra to come up with the value of P. So 1 over P minus 1 is equal to n0 by n1. I bring the minus 1 to the other side. So this becomes 1 over P is equal to n0 plus n1 by n1. Now we know that n0 plus n1 is the total number of trials. So P is basically n1 by capital N. Okay, so now what do we have here? The probability the head is 1 is simply the ratio of, okay, so the number of times head happened, number of heads in the trial divided by total number of trials. This is the probability of head. Okay, so this is very intuitive. So whenever I want, whenever I tell you, okay, for example, I tell you that I did 20 trials and 12 times it was head and 8 times it was tail. I ask you what is the probability that the next trial is going to be head, then the probability is simply 12 by 20, right? So now this is exactly what the maximum likelihood estimator is doing. Okay, now let's go back to the Bayes rule. And if we look at what we have done so far from this point of view, so we took P of x given theta and we were maximizing P of x given theta, right? But if we start thinking from the Bayesian way, then what we care a lot about is this P of theta given x. So given a data set, now what is the probability of theta given this data set? Okay, so now instead of maximizing the likelihood, one could actually maximize this posterior distribution and find the most reasonable theta, right? So now that is our second estimator. So our second estimator is called maximum a posteriori estimation, or MAP. Okay, so MAP basically allows you to include some a priori belief on the parameters by weighing with a prior distribution P of theta. Okay, so how do we do that? So in the case of MAP estimation, theta MAP is given by argmax of theta, probability of theta given x. Okay, so now this is equivalent to argmax of theta, probability of x given, x given theta, P of theta divided by P of x, right? Now, we see that P of x is independent of theta, right? So there is no use in adding this term when we are just maximizing over theta. So I could just remove it. So this becomes argmax over theta, P of x given theta, P of theta. Okay, so now I can actually compute a log of this term. So this becomes argmax over theta. If you take the log of the first term, which is the log likelihood, so you get L, the scripted L, plus log of P theta. Okay, so I could expand this further. So this becomes argmax of theta. The first term is summation over x belonging to x, log probability of x given theta, plus the second term is just log P of theta. Okay, now what is the difference between the maximum likelihood estimation and MAP estimation, right? So the only difference that you see here is this extra term, which is log probability of theta. Okay, now this is a very useful term because you can actually add any prior knowledge that you already have. For example, you could use this P of theta to encode extra knowledge that you want to encode. Okay, now you could even use this P of theta to prevent overfitting by enforcing preference to simpler models. Okay, now, so does this term ring a bell for you? So have we seen anything like this before? Any idea? Regularization, right? Like, so in the case of regularization, you had maximum log likelihood plus L2 regularization or L1 regularization, right? So now, what exactly was regularization doing? It was actually trying to prevent overfitting by preferring simpler models. When you do L2 regularization, the preference is to have as small magnitude as possible. When you have L1 regularization, the preference is to have sparser models, right? Like, so now this idea of preferring simpler models, I'm not sure if I have already discussed about Occam's razor in the course. Someone can remind me if I have or not. But Occam's razor is this basic idea that you should always prefer simpler models over complex models if the performance is same. Okay. Uh, any guess why that should be the case? I'm just claiming that we should always prefer simpler models over complex model, provided they have the same performance. Why? Any idea? To prevent overfitting, right? Like, so the complex model has the risk of overfitting. So we could actually avoid that if we just follow this Occam's razor. Okay, so now, in fact, this equation looking exactly or very much like L2 regularization or L1 regularization is not a coincidence, okay? So in next lecture, we will actually see that adding L1 regularization or L2 regularization has a Bayesian interpretation, like, and we will look at it in the next lecture, okay? So like, just wait for one more lecture. But let's continue with map, okay? So now map essentially follows the Bayesian approach, okay, where we consider theta as random variable and we set a prior to this theta, okay? So P of theta is the prior, right? So now this prior could have some parameters themselves. So P of theta given alpha, okay? Now this alpha, the prior parameter of the prior, is known as the hyperparameter, okay? Now let's go to the inference again. P of x given x, which is what we care about, right? So if you remember, if you recall, this is basically integral over theta belonging to capital theta, P of x given theta, P of theta given x dx, right? Now, the way in which map is approximating this is by simply computing P of x given theta map. Okay, is that clear? Okay, so now let's actually go back to our coin tossing example. Okay, so now I want to add a prior information, okay, that the coin is usually fair. So if so, what should be the value of P? What should be the value of P if my coin is usually fair? 0.5, right? So I want to come up with the P of theta. Okay, so now this is bad notation from my part. So probability of the parameter here is P. Okay, so I will try to differentiate the P's. So the probability of the parameter of Bernoulli P, right? So the P of P, I want this to have a high probability around 0.45. Okay. Also, I am interested in a distribution which has a support from 0 to 1 because P belongs to 0 to 1, right? Like P takes value from 0 to 1, right? Maybe inclusive. So I'm interested in a distribution which has a support of 0 to 1, okay? So there are many such distributions. We are going to just consider one such distribution, which is the beta distribution. Okay. Now, the probability of my parameter P given beta distribution has two variables, okay, two hyperparameters, okay, alpha and beta, is given by 1 over b of alpha beta p power alpha minus 1, 1 minus p power beta minus 1. Okay, now this is just the probability distribution for the beta distribution. This is beta of p given alpha beta. Okay, where the b function is given by gamma of alpha, gamma of beta, gamma of alpha plus beta. Okay, now I'm doing a lot of cyclic definitions here. So the gamma function, so this is called gamma function, and the gamma function is defined as simply x gamma is x minus 1 factorial. So I have just done a lot of chain definitions here, but so this is beta function or beta function, whatever way you call it. Okay, now this distribution has the support of 0 to 1. Okay, now for different values of alpha and beta, so this is how the distribution would look like. Oh, sorry. Okay, something happened. Okay. So for different values of alpha and beta, this is how the beta distribution would look like. Okay. So now you can see that whenever, like okay, so one thing to remember is if alpha is equal to beta, then the mode of the distribution is exactly at 0.5. You can see that this is beta of 4,4. Okay. Now you can see that as I increase this value, if this is 4, it's like this. If this is equal to 20, you can see that it's peaking around 0.5, right? So now depending on like other values, you could have a peak wherever you want. So for example, 10,30 gives a peak which is less than 0.5. Similarly, if you do 30,10, it's going to give you a peak in this direction. So you can choose any of these like alpha and beta, then that is going to give you a prior distribution. Okay. So now for our example, we are going to set alpha is equal to beta is equal to 5. Okay. Now this will result in a distribution which would look something like this, approximately. Is that clear? Okay. So now let's do map estimate, which is essentially dou by dou p of L plus log p of p. Right? So we have already differentiated for the log likelihood part, which was basically n1 over p minus n0 by 1 minus p, right? So now we should also differentiate log of the beta probability. So the beta probability is given here, right? So when you differentiate, like you're going to differentiate this, like you take a log of this. So the log of the first term, it has nothing to do with the parameter, so you can ignore it. But the log of the second term and third term, like would have my plus alpha minus 1 by p minus beta minus 1 by 1 minus p is equal to 0. I have directly written the derivatives here instead of doing the steps one by one. But by this time, you should have already gotten used to it. Okay, so now we just need to simplify this. We are going to get a value for p, right? So it's n1 plus alpha minus 1 by p is equal to n0 plus beta minus 1 by 1 minus p. Okay, now 1 minus p by p is equal to n0 plus beta minus 1 plus n1 plus alpha minus 1 divided by n1 plus alpha minus 1. Right? Now, okay, well, maybe I skipped a step, sorry. I think this is right. Okay. Now 1 over p minus 1 is equal to this. So I'm going to take the minus 1 to the other side. It becomes plus 1. So then it becomes n0 plus beta minus 1 plus n1 plus alpha minus 1 divided by n1 plus alpha minus 1. Okay. Now p map estimate is given by n1 plus alpha minus 1 divided by, if I just sum these two things, I'm going to get capital N. So N plus alpha plus beta minus 2. Okay. Now this is the formula for map estimation. Okay. Now let's compare this with my PMLE. What was my PMLE? It was just simply N1 divided by capital N, right? Okay. Now, can someone tell me what is the effect of adding this alpha and beta to my estimate? Think about it. Maybe let's just finish the numerical. So like P map is given by, in this case, we have alpha is equal to beta is equal to 5, right? So N1 plus 4 divided by N1 plus N0 plus 8. Okay. So now for the example that we had where N is equal to 20, N1 is equal to 12, N0 is equal to 8, the P map is given by 16 by 28, which is 0.571. Okay. On the other hand, the PML was given by 0.6. Okay. Now, looking at these values, can someone tell me what is the effect of alpha and beta? So what did alpha and beta do to our estimate? Okay. Someone say similar to smoothing, someone say safety margin, like any other answers? Any other answers? Okay, averaging near 0.5. Okay. See, if you think about how we set alpha and beta, we set alpha and beta in such a way that the mode is at 0.5, right? So in some sense, what this alpha and beta has done is it has pulled the value from 0.6 to towards 0.5, right? So in some sense, if you look at this equation, alpha, okay, maybe I'll rewrite this equation as well here. So P map is given by N1 plus alpha minus 1 divided by N plus alpha plus beta minus 2, right? Similarly, PMLE is given by N over N, right? Okay, so in some sense, alpha and beta are just adding some extra counts to N1 and N0, right? So N alpha is adding some, add alpha minus 1 to N1. Similarly, beta is adding beta minus 1 to N0, right? So it is, when I say alpha is equal to 5, beta is equal to 5, it is as if I tossed this coins 8 times before and 4 times it was head, 4 times it was tail. Okay, so we are going to call this alpha and beta as some sort of pseudo counts. So these are my counts even before the experiment started. Okay, so instead of starting with n1 is equal, n0 is equal to 0, n1 is equal to 0, I actually started with n0 is equal to 4 and n1 is equal to 4. Okay, now we also interpret the strength of this alpha and beta. So instead of starting with alpha is equal to beta is equal to 5, which gives me 4, 4, I could start with alpha is equal to beta is equal to 1000. Okay, now that gives a very strong message that it's a fair coin, right? So now if I have to overcome this value from 0.5 to let's say 0.6, I need to see tens of thousands of examples, or like more than thousands or 1,000 example at least. Like I have to see a lot of example to come out of this prior. Okay, so in some sense, you can actually tune your prior in such a way that you can put your solution in the space that you want. And at the same time, it is not very restrictive because Like if the data tells that your prior is not the right place, then after a lot of learning, your model can overcome that, given that it sees enough data, right? So now that is the interpretation for prior over the parameters. Okay, a quick note is if I do map with uniform prior over theta, then that is exactly what MLE is doing, right? So MLE is just putting uniform prior over all possible theta. And in reality, we know how the data arrived. So we might have some knowledge about the data. So we can actually use this knowledge and come up with a better predictor than MLE by incorporating these priors. Okay. So any questions about map estimation? No questions? Chat or hand raise? Okay, so we will continue. So now we are going to look at a much more general estimator, which is the Bayesian estimator. Okay, so there's a question. We basically have more samples. Okay, it's not like we have more samples. Okay, so it like we are also incorporating our prior knowledge to the model, like even before seeing any samples. So like, for example, like someone commented that this might be similar to smoothing, which is kind of true, right? Like, so if you remember Laplace smoothing, like we were adding +1 for all the words in the vocabulary, right? Like, so similarly, this is as if in this case, this is much more informed because I could add 4, 4, or I could also add 8, 4, which means it's more biased towards head, right? Like, or I could add 4, 8, which means it's more biased towards tail and so on. Is that clear? Okay, so now we are going to look at the third type of estimator, which is the Bayesian estimation. Okay, so this basically extends the map approach, okay, by allowing a distribution over theta instead of making a direct estimate. Okay, so instead of having a single value, we are going to model a distribution over theta. Okay, or in other words, we are actually going to use the complete Bayes rule. So P of theta given x is equal to P of x given theta, P of theta by P of x, right? So instead of just doing the maximum a posteriori estimation, we are going to directly maintain this distribution P of theta given x. Okay. However, this is much more harder thing to do when compared to the other two approaches, simply because this requires computation of this P of x, the normalization term, okay, which is nothing but integral over all possible theta, P of x given theta, P of theta, d theta, right? Now this integration is over all possible theta. So now this is a very complex integration to do. So this finding this integral is the intricate part of Bayesian learning. Okay, but once you have this, this is difficult to do. Okay, but once you do this, then you can actually compute P of x given x in a different way. So now in this case, it's going to be integral theta over theta, P of x given theta, P of theta given x, right? So now I can just write this as integral over theta belonging to theta, P of x given theta, P of capital X given theta, P of theta divided by P of x d theta. Okay. So now I'm not doing any approximations. In both MLE and MAP, I was doing some approximation of the inference process, right? Like, so now in this case, I'm not doing any approximation. I'm actually computing the exact P of X given X. Okay. Now, let's see how to do that with the same coin toss example. Okay. Now, what is the probability in the coin toss example? Like, we want to ask this question: what is the probability of P given the data set and alpha and beta? Okay. Now, this is simply product over I is equal to 1 to capital N, probability of C is equal to Ci given P. So now this is the likelihood term. I'm just doing the base rule here, okay? So now this is my posterior. This is my likelihood multiplied by the prior. The prior is probability of P given alpha beta. This is my prior, right? Divided by the evidence, which is integral over 0 to 1, product I is equal to 1 to capital N, P of C is equal to Ci given P, P of P given alpha beta dP, right? Okay. Now, let's try to compute this sum, like to this term, and see if we can come up with a closed form solution, okay? So now, it would be nice if we have the closed form solution for this, right? Like, if we have the closed form solution, then we have a more efficient way of doing these estimations, which is going to be better than the MLE or MAP that we have seen. Okay, so I'm just going to expand things here, okay? So now this becomes P power N1, 1 minus P power N0. So this is for the likelihood. Similarly, the prior is simply 1 over B of alpha beta, P power alpha minus 1, 1 minus P power beta minus 1, right? Now, if you look at the denominator, this is just a normalization constant, right? Like, so for now, let's not worry about computing this. Let's just call it as Z, okay? Now, I can do some simplifications here. So now this is basically P of N1 plus alpha minus 1, 1 minus P of N0 plus beta minus 1, divided by B of alpha beta multiplied by Z. Okay. Now, so this is my P of the parameter given C alpha beta. Well, I'm really sorry for using P for both probability and parameters. So probably next time when I edit the note, so I will fix it to some other, like just theta maybe. Okay. Now, the numerator looks familiar, right? Like, so now can someone tell me what kind of probability distribution could the numerator be? Bernoulli, anything else? Okay, anything else? Beta, okay. So now what is more probable, Bernoulli or beta? See, first of all, this is a probability distribution, right? So this has to be some distribution. So now what is more probable, Bernoulli or beta? Beta, right? So I will let you convince yourself, okay? So now this is actually equivalent to P of N1 plus alpha minus 1, 1 minus P of N0 plus beta minus 1 divided by this denominator, right? So now this denominator is actually beta of N1 plus alpha, N0 plus beta. So I will let you prove this as an exercise, okay? So essentially, this is just beta of P given N1 plus alpha, N0 plus beta. Okay. Now, this is beautiful. Why? because I started with, I'm interested in P of, like I'm interested in the posterior, okay, which is basically likelihood multiplied by prior divided by evidence. And I told you evidence is a very hard thing to compute, right? Now, we started with a Bernoulli likelihood and a beta prior, and without even computing the evidence, we have a closed form solution for posterior, which is also a beta, right? So now we know everything about beta distribution already. So if I have a beta of alpha beta, then the mean of beta distribution is given by alpha plus beta. Okay. The variance of this distribution is given by alpha plus beta plus 1, alpha plus beta, the whole square. You don't need to remember them by heart. Like, so it is just that we already have access to the mean and variance of the beta distribution. Okay. So now I can actually compute these quantities for the coin toss example. So the mean is going to be n1 plus alpha divided by n1 plus n0 plus alpha plus beta. If I use alpha is equal to beta is equal to 5, then this is simply n1 plus 5 divided by capital N plus 10. Similarly, the variance is given by n1 plus alpha, n0 plus beta divided by n plus alpha plus beta plus 1, n plus alpha plus beta, the whole square. So this is simply n1 plus 5, n0 plus 5 divided by n plus 11, n plus 10, the whole square. Okay. Now the first thing that we notice is this mean term is not the same as the map term that we had, right? So to recall you the map term, right? So we had, I'm going to put everything here so that, so the Emily estimate was given by, sorry, n0 by n, right? The map estimate was given by n1 plus alpha minus 1 by n plus alpha plus beta minus 2, right? On the other hand, the mean and variance for, so, okay, one thing to remember is both Emily and map are point estimates. They just give you one theta, right? On the other hand, this is not a point estimate. So P, okay, I don't know if I have a notation for the Bayesian thing. Let's just call P base. Okay. Now this has mean and variance. It's actually a complete distribution. Okay. Now if I compute these values for the same example that we have been following, n is equal to 20, n1 is equal to 12, n0 is equal to 8, the mean would be something around 0.567, and the variance is going to be something around 0.0079. Okay. So now we are going to compare all the three distributions that we have, the estimates that we have seen so far in this one picture. So here you can actually see that this red line is the maximum likelihood estimate for the coin toss example. Okay. Now this blue line is the map estimate. Now you can see that if I use the full Bayesian estimation, the expectation is a bit lower than the map. Okay. And we also have a variance. Okay. Now you can see that the green line is my prior distribution and the blue line is my posterior distribution. So after seeing 12 heads and 8 tail, my prior is slowly moving towards the head, right? And it is also getting more confident. That is why the probability is peaking. Do you get it? Okay. So now, the fact that I actually started with a Bernoulli likelihood and beta prior, and I ended up with a beautiful beta posterior is not a coincidence. Okay. I carefully chose the beta distribution so that the posterior has a closed form solution. Okay. Now this is well studied in the statistics literature. Okay. So this is basically the idea of conjugate distributions. Okay. Now, a conjugate prior P of theta of a likelihood P of x given theta is basically some distribution that results in a posterior distribution P of theta given x with same functional form as the prior. Okay. Now this is a beautiful concept because if I take a likelihood and I use the corresponding conjugate prior, then I don't need to compute the normalization constant, which is very difficult to compute. Okay, it's an integration over all possible theta, right? I can come up with an efficient like equation or formulation for the posterior. Okay, now as an example that we have seen, beta is a conjugate prior for Bernoulli. Okay, in fact, there are other, I can give you some other examples like binomial. So, okay, maybe I'll put it this way. So Bernoulli likelihood has beta prior. Okay, so even for binomial likelihood, beta is the conjugate prior. So if you have a multinomial likelihood, then Dirichlet function, Dirichlet random variable is the prior. Gaussian is always special, right? So when you have normal likelihood, can someone guess me? Can someone guess what would be the conjugate prior for normal distribution? It's normal itself. Okay, so when you have a normal likelihood, the conjugate prior is also normal. Okay, so now, as I said, this idea of conjugate priors is well established, and now there is a question, right? Like, so can I find a conjugate prior for every likelihood function that I have? Okay, so the answer is no. You cannot find a conjugate prior for every possible distribution. However, there exists this family of distributions called exponential family. Okay, so this is a special family of distributions with the property that conjugate prior exists for all the members of this family. Okay, so conjugate prior exists for all members of the exponential family. And Bernoulli, binomial, multinomial, normal, all these functions are members of the exponential family. Okay. Now, this idea of conjugate priors has several advantages. Let's go over some of them. Okay. So the first main advantage is finding normalization term. 1 over z is simple. We don't need to worry about normalization term at all, right? Like, because now we know that we can come up with a closed form solution. Second of all, it gives more meaningful interpretation of hyperparameters. Okay, so that is why in the case of beta Bernoulli, we had an interpretation. What was the interpretation? So alpha and beta are basically some pseudo counts, right? Like, we can have such interpretation for every conjugate prior. Okay, now there is also another very useful property of conjugate priors, which is the idea that it often allows us to marginalize out the parameters at all in closed form. Okay, so it helps us, or it allows us to marginalize out the parameters in closed form. Okay, and thus express the likelihood of observations directly in terms of hyperparameters. If you have a conjugate prior, you can actually marginalize out the parameters and directly compute the probability of like your likelihood by using just hyperparameters. Okay, let me give you an example. So let's go back to the same beta Bernoulli case. Now the probability of C given alpha beta, right? This is the likelihood, is given by integral over 0 to 1, probability of C given P, probability of P given alpha beta dP, right? Now this is given by integral over 0 to 1, P power n1, 1 minus P power n0, 1 over P of alpha beta, P power alpha minus 1, 1 minus P power beta minus 1 dP, right? So now this becomes, I can just bring the beta outside, like B function outside. So this becomes integral 0 to 1, P power n1 plus alpha minus 1, 1 minus P power n0 plus beta minus 1 dP, right? Now what is this integral? This integral is the denominator of another beta function, like another beta distribution, right? So now this integral is essentially, like I'll just put the first integral, which is this. The second integral is essentially beta of n1 plus alpha, n0 plus beta. Okay. So now what have I done here? I'm computing the likelihood. I completely removed the parameter P. So there is just alphas and betas and examples. So now the probability of C given alpha beta is given by, simply given by this beta of n1 plus alpha, n0 plus beta divided by beta of alpha comma beta. Okay, I have expanded this in the notes. You can go check. Okay, so maybe I'll just do the expansion here. So this is simply n1 plus alpha, n0 plus beta, alpha plus beta divided by n1 plus n0 plus alpha plus beta, alpha beta. I have just expanded both the beta functions. Okay, so now what is the advantage of this? The advantage of this is like now I can actually use this to directly compute P of new example is equal to 1 given C alpha beta. Okay, so now again I want to highlight that there is no parameter here. There is just hyperparameter and the data. And now I'm representing my model by just using the hyperparameter. Okay, so now in this case, this is nothing but P of C is equal to 1 comma C given alpha beta divided by P of C given alpha beta, right? Simple probability equation. So now we have equation for this in the top, right? So I could just write this as n1 plus 1 plus alpha divided by n1 plus 1 plus n0 plus alpha plus beta. Okay, this is for the first term based on this equation. Okay, based on this equation, I'm just removing the alpha beta terms because it's going to cancel out. So the rest is given by n1 plus alpha divided by n1 plus n0 plus alpha plus beta. Okay, so all I have done here is I have just substituted this equation for 2 times here. Now this has a very simple form, which is n1 plus alpha divided by n1 plus n0 plus alpha plus beta. Okay, so now you can see that as you give me more data, I can integrate the data over this equation and make the next prediction. Is that clear? Okay, so I know we are running out of time, but I just want to end with the importance of Bayesian estimation. So why do we need, for the next couple of lectures, we are going to revisit the algorithms that we have already learned in this course and do a Bayesian treatment for those algorithms. Okay, so why Bayesian? Well, maybe I can do this in the next lecture as well. So let's just stop here. So we will discuss the importance of the Bayesian approach in the next lecture, and also revisit linear regression and other algorithms that we have seen so far, and like see how can we adapt them for Bayesian setting. So we will stop here. Any questions before I stop the recording? Any questions? Okay, so if there are no questions, we will stop the recording. Thank you.